Okay, yeah, so good afternoon and welcome to this presentation on how do we define good practice for fire and gas mapping. So yeah, focusing on the new British Standard BS60080 2020. Yeah, just like to start by saying thanks to Dave and the Institute of Measurement and Control for inviting me to talk today. So yeah, Dave gave me an introduction, and as he said, my kind of background is in consequence modelling and quantitative risk analysis, using various different techniques from phenomenological, which was the word that Dave was struggling with, through to computational fluid dynamics techniques using things like packages like FLAX and ANSYS CFX. So I got into kind of fire and gas detector mapping about 10 or 12 years ago. So started using computational fluid dynamics techniques to improve detector layouts, and then was also involved with the development of flame detector mapping software using raycasting techniques. In terms of what I'm going to talk about today, so first of all, I'm going to start with kind of a history of fire and gas detector mapping, the scope of the British Standard, a description of the workflow within the document, and then kind of key points to consider when you're approaching this kind of work. Just in terms of a history of fire and gas detector mapping and kind of where it all started. So it dates back to the 1800s, and believe it or not, the use of canaries in the coal industry to detect carbon monoxide levels. Obviously not a particularly humane solution or sustainable solution. So going forward from that point, there's a significant development in technology. A lot of the technologies that we see today, from catalytics to infrared to UV technology. Around this time, a lot of focus on ultimately functioning on demand. So if the detector could see the fire, or if the gas got to the detector head, ensuring that the relevant signal was generated. The 80s really saw the kind of first sort of formal definition and introduction of fire and gas detector mapping, and this was driven by the kind of oil and gas majors, so the likes of BP and Shell starting to develop guidance documents and internal standards. Moving forward to the 90s, especially in the process safety industry, there's a big push towards more quantitative analysis. So some of this came from the Cullen inquiry into the Piper Alpha disaster, and so we saw studies such as quantitative risk assessment, temporary refuse impairment assessment offshore, and occupied buildings risk assessment. Also, we then saw this quantitative analysis really develop into the fire and gas detector mapping arena as well, and a lot more development in more quantitative techniques in fire and gas detector mapping. Moving forward into the kind of 2000s, we saw a significant develop in both the ability to develop software and also computing resources. And so effectively during this time, we saw a lot of the development of lots of different software packages and solutions for fire and gas detector mapping, and almost it becoming a market in its own right, with lots of different consultancies offering the service, and like I say, lots of different software packages competing against each other as well. So the question is, where are we today in 2021? So despite fire and gas detector mapping being around for nearly 30 years, before this British standard, there was still really limited guidance on the topic. This led to kind of two main problems. So without formal definition, effectively, how can we say that we know what good practice is? Within the UK and the legislative regime that we work in, we work to the ALARP principle. One of the key principles of ALARP is to demonstrate that we are following relevant good practice. If there is no relevant good practice around, it's then very difficult to essentially have that demonstration that our solution to a particular hazard is ALARP. And then secondly, without this formal guidance, we also lack consistency within the area of fire and gas detector mapping, and so you get two very different solutions going to two different parties. One argument is that, is this actually a point of concern? Is not detecting fires and not detecting gaseous releases, is this an issue effectively in industry? The best source of data to really analyse this is the offshore industry, which are quite rigorous in the way that it records and kind of investigates the incidents that do occur. And so a study that was conducted by the HSE showed that 36% of major gas releases and 69% of significant gas releases went undetected. And it's even more for two-phase releases. So this kind of highlights that essentially there is a problem. In terms of the current guidance that's out there at the moment before this British standard, within 679.29-2, there's quite generic guidance, probably 3/4 of a page with 10 to 12 bullet points that detailing some factors to consider, but it's not really sufficient to base a gas detector or fire detector analysis on. Similarly, within the HSE website, there's some guidance on in the COMA section, but again, it's not extensive. One of the most kind of extensively used and detailed documents that is available is ISATR 84. This talks about volumetric and scenario-based mapping, which I'll go into in more detail later. But feedback is that in some instances it can be quite difficult to implement. This has got a very much a kind of functional safety biased the way that it's developed and written. And it also doesn't really focus on toxics at all. It gives very limited guidance on toxics. It's really focused on flammables. An extract from the BP document, GP 3085, just kind of recognises that before this British standard there was limited international or national guidance available, and so consequently this is really why the British standard was developed in the first place, to address this issue and effectively plug this gap. In terms of the title, this is the title, and these are the committee members that were involved. So as you can see, there was a range of different backgrounds, from operators to fire and gas detector manufacturers and to consultants like myself, and then also some input from the HSE. The scope of the document, so essentially it covers fixed gas detection, so there's limited guidance on portable or personal detection, and it covers flammables, toxics, asphyxiants, and elevated or oxygen enriched environments. There's also guidance on operations and maintenance, so it's not just around conducting your fire and gas detector mapping at the design stage, but it gives guidance on how you manage it, your fire and gas detector system through the kind of life cycle of your facility. So what is out of scope? Essentially, it's a new standard. We started with a blank piece of paper, so there was a significant amount of effort almost just to get to a first draft. So to try and make or reduce the work to a kind of practical level so we could get something out in some reasonable timescales, there were a number of areas where we decided not to focus on in this first edition for various reasons. For example, misdetection. This is still, from a technology point of view, this is still in its infancy, and so when we were developing the British standard, the HSE were doing a lot of work on understanding the practical detection envelope of misdetection with respect to things like droplet sizes, because there was uncertainty around the actual technology, we didn't feel like we could really be in a position to offer guidance in the mapping for mist detection at this time. Smoke detection, another one that was not covered for a different reason. A lot smoke detection tends to be quite prescriptive, and so and is covered in other British standards. So it wasn't felt that we needed to kind of repeat that here. Area kind of pertinent to probably a lot of the audience today is reliability, so safety integrity levels, and this is often a kind of point of contention within fire and gas detection systems. And so again, there's limited guidance in the document on safety integrity levels, and but I'll talk a little bit more about that as we go through. And then finally, just to say that the document itself doesn't focus on one particular industry. It's written from a generic point of view, and it should be equally applicable to any industry that handles flammables, toxics, or asphyxiant gases or vapours. So the type of British standards, so there's three types: a guide, a specification, or a code of practice. This document's a guide. In terms of the reason for this is because it's very hard to be prescriptive with respect to fire and gas detector mapping, because there's not necessarily a right or wrong answer. A lot of it comes down to kind of risk acceptance, because I hate to kind of draw parallels to Corona, but you can draw parallels in this instance, because with respect to Corona, especially within the UK, we're never going to get effectively down to a COVID zero kind of state. So we're always going to have to live with a residual level of risk associated with Corona in our day-to-day life, and people have different almost perceptions and acceptability criteria to what they deem is an acceptable level. And to a certain extent, it's similar with fire and gas detection. You're never going to be able to detect absolutely every release within your facility, and so you have to define an acceptability with respect to what level of risk you are willing to tolerate, and that will obviously that will differ from operator to operator and what you're trying to protect against. So that's really the reason why the document can't be prescriptive, and it just has to almost set out a framework and guide the kind of user as to what they should be considering. So in terms of the discussions that we had when we were going through the development of the document, one of the key points that we kept kind of reiterating if we got sort of off topic is the discussions we're having, do they relate to how many detectors I need and where I need to put them? And if the answer to that question was no, then ultimately those discussions were considered out of scope, and that kind of information didn't go into the document. So hopefully, if you join this call today, this is the kind of answers that you've been asking yourself on your particular project, because this is kind of the crux of the document and what it essentially tries to address. So yeah, before I get into some detail, just a little bit of context on flame and gas detectors. So this is a bow tie where you have a hazard in the middle, you have the threats on the left hand side, and you have preventative barriers on the left and recovery barriers on the right hand side. So it's just to really stress that fire and gas detection very much lies on the right hand side of a bow tie. So it's a recovery or a mitigation barrier, and unlike some other safety instrumented systems, it in isolation it only actually detects the hazards, it doesn't actually prevent it, and so it has to be combined with additional risk reduction. So for example, blowdown, deluge, alarms that actually act to either reduce the potential for escalation or increase the chance for escape and evacuation. And so some of the reasons why safety integrity levels are kind of harder to define for these kind of systems relate to this kind of problem, because in some instances, even if you're gas detection system works 100% as it's supposed to effectively, dependent if you get your ignition before your gas detection functions, then you've not actually reduced the risk at all. And also, even if you're also got a finite amount of time once all your system has effectively functioned, if you're to isolate and blow down, where you've still got a release of gas that effectively has to depressurize until your hazard can no longer be realized as well. Yeah, so now getting into the kind of some of the detail about the document itself. So this gives a kind of brief sort of overview on the kind of different sections in the document. So today I'm going to focus on mainly the black ones there, the ones that are grayed out. There are sections in the document, but I'm not going to cover these in any detail. So the document itself kind of hinges around this kind of workflow that you can see here. I appreciate you probably can't read that due to the size, but I'm going to kind of zoom in and focus on different areas on the subsequent slides. So firstly, the actual philosophy. So there's a number of inputs and outputs that go into defining this philosophy. And again, I'll go into more detail on these now. So the starting point, like with many safety studies, is ultimately the hazard identification and the risk assessment. So the document itself doesn't give detailed guidance on risk assessment because this is covered in numerous other HSE documents and British standards. But essentially the starting point for effectively using this document is that you've gone through that risk assessment process, and in order to demonstrate that your risks are as low as reasonably practicable, you have made the decision that you feel you need fire or gas detection. One point to consider at this stage is that you need to really decide what your fire and gas detection system is protecting against, though. So are you protecting against personnel? Are you protecting against environmental hazards? Are you protecting against business continuity or asset protection? Or is it a combination of each of those four different aspects? And so essentially you should really be designing your system for the most onerous of those cases. In terms of inputs, one of the key things is to ensure that, like when you're conducting studies like hazards or HAZOPs, is that essentially you get buy-in from the multidisciplinary team. The standard talks about many different competency areas, and yeah, it's obviously just by today, I've got a process safety background, but obviously there's many other stakeholders involved. So instrumentation and control obviously being one of them, operations, maintenance, to name but a few. And so it's really just to stress that up front, it's key to get all those stakeholders involved and make sure that they buy into the philosophy of the fire and gas detection system. And so it's unlikely that it's going to be conducted similar to a HAZOP, kind of like within a workshop, but at least again at that early stage should make sure that key stakeholders are consulted, because otherwise you can get yourself in a situation where effectively you end up repeating the analysis multiple times if people have different views on the approaches that they want to take. And obviously this can be both time consuming and expensive. In terms of the output, you essentially would, at this stage, you define your fire and gas philosophy or strategy. So if there's any fire engineers on the call, so this is, I guess, similar to how you would define a fire strategy for a commercial or a residential building. And so this is kind of one of my sort of hobby horses, because a lot of the projects I work on, I see that this has never really been developed, and the only kind of output that you have from these studies in a lot of instances is essentially the layout, which says very little about the philosophy and the strategy for the design. So yeah, it's important for many reasons. It fundamentally documents your thought thought process. It allows consistency for modifications in the future. And I think it guards against this kind of tendency. Now we have a lot more kind of tools and a lot more software packages that we can use. I think often there's a temptation to just jump into detail. Let's just start calculating things and feel like that's gonna give us progress. But ultimately, it's trying to stress that before you kind of start these calculations and go into the detail, to almost take a step back and ensure that you understand why your gas detection or fire detection system is there in the first place, and what you're trying to achieve. So this document as well, it should be a live document, so it's not, especially for a new project, so it's not necessarily going to be a case of you write it once and never touch it again. But as the design progresses, you may update it because you might use different mapping techniques, because you've got more detail available as the design becomes more mature. And so the kind of aspects that you want to cover are the metrics that you're going to use to assess your system, and technologies for your environment and hazard, and things like the set points for your detectors also. Now moving on to a little bit more detail on the methodologies themselves. So there's 3 different methodologies described within the document: prescriptive mapping, volumetric, also often referred to as geographic, and scenario-based mapping, again sometimes referred to as risk-based mapping as well. In terms of the level of complexity, essentially the level of complexity increases as you go from prescriptive through to scenario mapping. And in terms of which methodology you should be employing, it really comes down to proportionality. So understanding that the risk associated with your particular application. So in cases or facilities that have got much more significant risk, then a scenario mapping approach is potentially beneficial. But if it's a low risk and effectively quite a simple system, qualitative or prescriptive methods may be applicable. So this is kind of similar to the guidance you get with respect to the control of major accident hazards and the risk assessment associated with quantifying major accident hazards. So if you've got effectively a low risk facility, you wouldn't go to hugely detailed quantitative risk assessment. That's when more qualitative techniques would be applicable, and it's a similar thought process here. In terms of a little bit more detail about what we define as prescriptive, so like I said, it's prescriptive really is qualitative methods, and where it lends itself to this is kind of simple systems. So for example, for fire detection, if you had a very open room with minimal actual instances where you could get a fire, it may be sufficient to just locate your detectors at the extremities of the room and point those towards the actual the fire hazard itself, and it wouldn't be necessary to go to a software-based solution using raycasting techniques. Similarly for gas detection, if you had a single inventory, a pipe run, just one kind of inventory in a particular room or facility, and you have for example, a very predefined airflow, for example, via a HVAC system. Just by understanding the nature of the release, so the buoyancy and the ventilation within that room, you could come to a pragmatic solution as to what the most appropriate place to place the detectors, again without having to go to a hugely detailed volumetric or scenario-based approach. And then the other example there is proven design. So you might have done a very detailed study previously for a particular facility, and you're effectively making designing a very similar facility. So you could use the learnings from that previous design and apply those to the new design, again without having to go to detailed mapping methods. So moving on to volumetric. So this is a semi-quantitative method. So essentially it looks at the volume and it predicts the coverage in terms of volume of a particular fire or cloud size and presents the results as a percentage of that area. In its most simplest form, it doesn't really take credit for where fires or gas releases are likely to originate and assumes that they could effectively happen in anywhere within that three-dimensional space. In terms of a very simple 2D example, if you were trying to analyze this 2D space, you had two detectors, you had a target gas cloud size of 5 meters. If you had a release here, this wouldn't, in this instance, if it was a 5 meter cloud, get detected. And so in terms of quantifying the metrics associated with this particular example, the coverage is effectively the area of those two circles divided by the total area of the rectangle. So in this instance, approximately 10.4%. Just in terms of a actual more practical example, this shows that a point detector in green, the sphere, and a cylinder shown by a line of sight detector. And this shows the results of this particular analysis. So you've got control action, which is the action of two detectors, alarm via one detector, and no coverage shown in red by the 10% coverage. And so the slices at various different elevations through this domain that are illustrated in this plot. And again, just another picture here, just a particular elevation, again showing the different coverage of one detector, two detectors, and no detectors. So scenario-based mapping. So this is effectively a fully quantitative method. You are postulating different scenarios. You have frequencies of these scenarios, and then the results are actually presented in terms of either the percentage of the cases that are detected or the frequency of cases that are detected or not detected. And so in this instance, you're simulating actual scenarios. So you're looking at where the likely release locations are going to be. You're simulating different compositions, different pressures, different hole sizes, different wind conditions, representative of the facility that you're analysing. Again, just in terms of a simple 2D example, again, within this rectangle now we've superimposed a pipe run and some valves, and we have 2 point detectors and a line of sight detectors, and assuming that very simplistically any release is going to be spherical, we can postulate releases along this pipe run and assess whether or not they are detected or not detected by our gas detection system. In this instance, this example shows that effectively 50% of the cases are detected. And similarly, you can present the results in terms of the frequency of undetected releases. So essentially summing the frequency of all of those cases that don't get detected. In terms of the applicability of these different techniques to the detection of flammables, fires, and toxics, essentially for flammable gas, each of these techniques are equally applicable. And like I mentioned previously, it's really down to the proportionality and the advantages and disadvantages of the methods as well, which I'll come on to shortly. In terms of fire, really it's only really the prescriptive and the volumetric mapping that are really appropriate at this time. There's a couple of reasons for that. The first is that scenario mapping is not applicable because for fire modeling there's a lot of there's a lot of complex phenomena that have to be solved to model fires accurately enough to predict how fire detectors are going to respond. So, for example, you've got to model the combustion process with respect to the amount of fuel and air that is going to be present. You've got to model the radiation. You've got to model the heat transfer. And at the moment, even with computational fluid dynamics and the amount of computing power that we have, there's almost too much uncertainty to be able to predict, to be able to simulate the fires for scenario mapping in sufficient detail. The second kind of issue is that the actual fire detectors themselves, again, there's not enough data on how they almost react to what we'd class as sort of real world fires, or the whole range of fires that you'd likely to have to model if you're going to take a scenario based mapping approach. So within the British Standard, it's really, there's just a word of warning really is as to if you are going to adopt a scenario based mapping approach for fires, then you have to be kind of very careful that you're not pushing at both the modelling capabilities or the fundamental understanding of how the detectors respond outside of their essential range of validity. With respect to toxics, the kind of most applicable methods are prescriptive or scenario based. So the reason for that is because toxic and harm is related not to volume but to concentrations at a given point, and not just at any instance in time. Effectively, how that concentration builds up over time, and effectively the dose that is going to be absorbed effectively by a particular individual. So you could have a very, very large volume of gas, but if it was a low concentration or very short-lived, then it wouldn't necessarily be a hazard. Whereas obviously with flammables, we're really worried about this volume of cloud building up, because obviously if that volume ignites and it's a significant volume, then that's when we get an explosion and propagation and significant overpressures. So essentially, you do see volumetric mapping sometimes used in toxic, but really that's really focused on when you have almost a set detector spacing that you're trying to achieve. So for example, I want detectors every 5 meters, and you can use the volumetric mapping as a technique to achieve that kind of performance criteria. But the actual concept, to a certain extent, of volumetric mapping is almost at odds as to the harm that you realize from if you are to have a toxic gas release. In terms of the advantages and disadvantages of methods, obviously prescriptive is kind of fast because there's no quantitative analysis, but because there's no quantification, it's potentially subjective. Volumetric mapping is still quite a fast technique. There's not a significant amount of computer processing or pre-processing that we need to perform for the modelling. Some of the disadvantages are that, like I've alluded to previously, in its most simplest form, the gas cloud or fire is assumed to originate anywhere within the volume that you're looking to assess, which sometimes can be a kind of too much of a simplification. And the other thing to note is that is sometimes kind of lost on people is that the volume coverage that's provided when you conduct volumetric mapping, this is not actually a probability of detection. And the main reason for that is because you're not actually modelling particular scenarios, you can't draw a direct parallel between coverage and probability of detection. The only thing that you can conclude is that the higher the coverage, it's indicative that you have a higher probability of detection, but it's very difficult to actually draw a kind of mathematical function between those two variables due to the nature of the way that volumetric mapping is carried out. So scenario mapping, that's it's obviously a more thorough consideration of the risk, but ultimately it's more time consuming, it's expensive, and it involves a greater level of competency and also potentially uncertainty because of the level of input information required, and also it can be dependent on the number of scenarios analysed, and I'll kind of talk about that particular aspect in a little more detail as we progress. So yeah, that concludes the section on the actual methodologies themselves, and hopefully give you some background on the different methodologies, advantages, disadvantages. So now I'll move on to the kind of some key points on the analysis of the results and things to consider. So the first point I'm going to talk about is a target gas cloud size for flammable gas detection. So historically, you will see you see a 5 meter by 5 meter grid used. The origins of this is some work done by the HSE in 1993. So this looked at a 6 meter cloud and showed that if this were to ignite, you wouldn't get overpressures greater than 150 millibar. One question to ask is, should this value effectively always be used? Some of the key points to consider for your particular facility is that does my plant or facility kind of reflect the experiments that were carried out? So, for example, these experiments were done for methane. If your plant's handling hydrogen, you potentially need a much smaller grid because hydrogen is much more energetic substance, and if you had a 6 meter cloud of hydrogen, it would be expected that you'd get more significant overpressures than 150 millibar. The second thing to think about is 150 millibar appropriate for my plant? So 150 millibar is kind of a typical overpressure that you expect to lead to personnel fatalities due to missiles generated in an explosion event. Sometimes that might not be almost the aim of your gas detection system. Your gas detection system may be looking to detect cloud sizes that are going to protect personnel inside a particular building or on the other side of a blast wall. And so you might be setting your criteria based on effectively the withstand of that blast wall or the withstand of that building, which in some instances could be over 1 bar or 2 bar, for example. And so therefore you could tolerate much larger gas cloud sizes. The other thing to consider is, this 150 millibar, like I said, it really is associated with personnel. But again, if you're designing your system to protect against consequences to the environment or business continuity, so for example, you have a key vessel or a key piece of equipment that you need to ensure is continuously running effectively, then you might again want to set your criteria associated with the overpressures that's going to lead to damage to that particular equipment, and again, this 150 millibar criteria might not be suitable. And the final point to really consider is which kind of events actually give me a 5 meter by 5 meter gas cloud if this is the route I want to take, because in some instances the pressures associated with your system, the confinement, the ventilation might just mean that it's not actually possible to get a cloud size that is that large for your potential particular configuration, or you might find that this kind of event is effectively a catastrophic release, and you might have other mitigation measures in place that are effectively going to detect that release, and therefore your gas detection system would give you limited benefit. So these are all kind of points to consider when you're setting your target gas cloud size. And so this target gas cloud size is can apply to both prescriptive, volumetric, and scenario-based mapping approaches. If you don't think it's appropriate, you've got a number of different options. So you can use judgment to effectively have a larger or smaller gas cloud size. You can use semi-quantitative techniques, so you could use things like the multi-energy method potentially if you're looking at overpressures potentially in the far field, or potentially some of the shell models like the scope model if you're looking at more local overpressures that you're looking to protect against, to understand what kind of cloud size you should be designing your system for, or the kind of the fully quantitative approaches to go to CFD explosion modeling. And so I guess it's key to stress here that the use of CFD here is different to the use of CFD in scenario mapping. So this is really focusing on explosion modeling. So this is understanding, essentially igniting a range of different cloud sizes and understanding what size cloud would lead to the overpressure that I'm trying to protect against. Now moving on to performance requirements and kind of this desire to work to an absolute number. So one thing that we often see is that almost there's an arbitrary number that people try and achieve, and there's no written guidance in any of the or no justification in any of the kind of guidance documents or papers that are around as to what kind of numbers you should be looking to achieve with your fire and gas detection system. But individuals or companies often work to a number in somewhat of an arbitrary manner. So it might be 85%, it may be 90%, but what you do see is that people just think that I've got to just hit this number. And so, for example, they'll hit 90%, but then why is effectively 89.999 not safe, but 90% is? And it's very hard to argue that you've done an alert demonstration just to hit one particular number. So what the document does is, unfortunately, the document doesn't give, I think one of the criticisms we've had as a document is that it doesn't give a number to aim for. I think there's more work to be done in this area, I think, to be able to substantiate any numbers that you would provide. And I think, again, with the timescales of the British Standard, we just ultimately didn't have the time to kind of be able to substantiate numbers that we were to include. So consequently, what we have done is to say that really what you should be doing is you should be understanding effectively when your results kind of level out. So in this example here, it shows that the blue line, once you've got to kind of 15 or 16 detectors, you're not actually getting significantly increased detector coverage. So this would be a justification that we feel that the number of detectors that we have is appropriate. It is effectively an ALARP solution. Whereas for the red line, where you can see that the gradient is effectively still increasing or the coverage is still increasing as you add more detectors, then in this instance, it's harder to argue that you've got an ALARP solution. A similar story for if you were to conduct scenario mapping and presenting the results either in terms of the percentage of scenarios detected or the frequency of releases undetected. The other benefit of going to scenario-based mapping is that because you've got an actual frequency of releases, you could actually or you can actually conduct cost-benefit analysis to understand the kind of value that you're getting for adding additional detectors. So you could look at the potential loss of life associated with the addition of extra detectors against the cost of those detectors, both in terms of installation costs and life cycle costs, to kind of to justify whether or not you should be adding additional detectors. The other thing to just stress, though, as well, if you're going to be conducting scenario mapping, you shouldn't just blindly, I don't think, just say, oh, it's okay to not detect these particular scenarios, because we're going for this potential target, you should always really be looking to understand what are those scenarios that are going undetected, because just in case they are the low frequency, very, very kind of high consequence events that are going to be leading to kind of multiple fatality. So really just to understand that.
Tim, just before you move off this slide, we've had a question. What do the red and blue lines represent?
Okay, so red represents what I would say is a solution where if you were to plot your results, you would still need more detectors, because effectively the grey, you've not flattened out that curve. So what you're trying to do and you're trying to demonstrate is that effectively as you add more and more detectors, you're not getting any sort of benefit in terms of increased coverage. So these are purely illustrative lines to kind of illustrate that point, and that you shouldn't just be looking to, like I say, just hit a number and then just be like, yeah, there I've got effectively an alarm solution by just demonstrating that you've exceeded one particular number.
So the flatter the line, the better from a coverage perspective.
Yes. Yeah, just a few more slides now on again, not just kind of being a slave to the numbers, for want of a better description, and really understanding your results. So again, this is a 2D example, and so I quite like chess, so I thought this is a good way to present the results. So this shows that the black, this illustrative example again shows that in black is a particular area where you have coverage, and white is an area where you're not covered. And so for this particular example, effectively the largest fire that you can go undetected is one that can fit in that square, essentially. But then now considering the same 2D space, this again has a 50% coverage, but in this instance, effectively, you can have a much larger fire and then hence much more significant consequences. And so it's really to stress that don't just turn it into a number crunching exercise and actually understand the results that you're getting, because it's more than just aiming for a particular number. So this just shows the comparisons between the two. And again, an actual kind of almost real world example. So in this example here, the red shows no coverage, and again, it shows that this area is actually quite significant in terms of it's an area where you could get quite a large undetected fire. But what you would need to do in this instance is actually understand, is there a potential for a fire in this actual area? Because again, in this volumetric mapping type approach, this is not necessarily something that's considered, i.e. where the fire originates. So it's combining both the numbers and also the kind of experience and the reviewing of the results to ensure that you're effectively coming to the most appropriate solution. Now, just a couple of points on scenario justification. So this is probably one of the biggest kind of criticisms of scenario-based mapping is how many scenarios do I need to model? And I guess the kind of, if you're in the camp of I don't like risk-based modeling, I don't like scenario-based mapping, then there's also the kind of the train of thought that often people conduct scenario-based mapping if they don't want to actually put many detectors in, and they potentially game the system to only simulate the scenarios that are going to show that the gas detection system is successful and don't consider the full range. So ultimately, there's effectively an infinite number of scenarios that you could simulate, because there's infinite number of leak directions, locations, sizes, wind speeds, wind directions, pressures and temperatures. So what you've got to try and do is you've got to discretize each of those variables and analyze a range of each of those different variables, and it's key to just ensure that the results and the layouts that you propose and design are effectively independent of the scenarios that you've considered. And so again, the standard doesn't give or it's not possible at the time at the moment to give definitive guidance as to how many scenarios that you need to consider, because that will depend on the size of your facility, the number of inventories within your facilities, the nature of your windrows. Because if you had a windrows or a facility where the wind was coming from a predominant direction, you could argue that you need to model less scenarios than one where it's very much more evenly spread. But really, the point that the document tries to push home is that you need to be able to demonstrate that your results are independent of the number of scenarios that you've analysed. And so, again, this is just an illustrative graph of how you could potentially demonstrate this. But it's essentially showing that as you simulate more and more scenarios for a given gas detection system, your curves should effectively flatten off, and you shouldn't your results shouldn't be changing. So your coverage percentages or percentage of cases that go undetected shouldn't be changing with the number of scenarios that you analyze. So in reality, this graph might not follow such a nice smooth curve. It could come up, could come down, but effectively, as you model more and more scenarios, you should effectively converge on a given value for detector coverage, and you should be able to demonstrate that you've done that for the scenarios that you've analysed. So in summary, I think again, one of the criticisms they had that I guess people thought this document was going to be quite prescriptive and tell them all the answers. Unfortunately, it's not a silver bullet. It doesn't give you all the answers, but what it tries to do, it tries to kind of develop a workflow and at least highlight all the key points that you should be considering to ensure that you've got a robust solution, and that you can go towards demonstrating that solution is a LARP. And yeah, so I guess it's really because there is essentially no right, is why we can't be so prescriptive, because it comes down to risk acceptance to a certain extent, and also just due to the variability of all the different plants and facilities that handle these kinds of materials. So yeah, that's a very quick high level overview of some of the kind of key points, but obviously there's a lot more information in the standard as well, and so it's now available. You can purchase it from the British Standards website. So I hope you found that helpful. Covered quite a lot, some things in detail, some things probably not in quite